what I want to point out here is I said linear and angular, they are always different. This is very important. Dimension of linear um, quantity and angular quantity, they are always different, except for frequency and angular frequency. So it's very important to note this. The dimension of linear quantity and angular quantity are always different, except for what? Angular frequency and frequency. For example, for distance, linear distance equals to what? Radius times what? Angular distance. Now, linear distance, the dimension is L. We all know that the dimension is L. But angular distance, the dimension, remember we said the angular distance, there was supplementary what? Angles. And it's measured in radian. Radian is dimensionless. It does not have dimension. Okay. So that's just it. This one is L. This one does not have what? Dimension. Now for velocity, the dimension of velocity is Lt minus 1. While dimension of angular velocity is what? Just t minus 1. Can you see the difference? So it's different from each other. Now, dimension of acceleration is what? Lt minus 2. While dimension of angular acceleration, remember angular acceleration is change in what? Change in angular velocity over what? Over change in time. And angular velocity itself is what? T minus 1 over what? Over t. That's what? T minus what? Equals to t minus 2. So angular acceleration is t minus 2, while linear acceleration is what? Lt minus 2. Now frequency, angular frequency is t minus 1, while frequency is t minus 1. Angular frequency is also what? T, sorry. Angular frequency is t minus, frequency is t minus 1. Angular frequency itself is what? Itself is t minus 1. Okay. Now, the formula, you can see the pattern that S equals to R theta, V equals to WR, acceleration is alpha R. But in angular momentum, please, you have to know this. The formula is different. It's different for what we are doing since. Okay? L equals to what? RP. That is the angular. Look at the formula. Linear distance is always R sub t. S equals to R theta, V equals to WR. Linear distance is always angular times radius until you get to angular frequency, angular momentum. Angular momentum is now the inverse of what we are doing since. Okay, so angular momentum is ml2. Okay, that's ml2 t minus 1. That's angular momentum. While momentum is what? ml t minus 1. So it's different. So the only one that is the same is angular frequency and what? They can ask you this question. Angular frequency and frequency, they are the same. Angular distance and distance are never the same. Angular velocity and velocity, they are not the same. Angular acceleration and acceleration, they are not the same. Okay. The only one that is the same is angular frequency and frequency. Angular momentum and momentum too, they are not the same. And I want you to note this. S, the linear is always equals to the radius times what? Angular. For distance is like that. For velocity is like that. For acceleration is like that. But for momentum it's not like that. Okay, just note it please. Okay, so let's now go to constant. Dimension of constant. We'll treat three constant now. The first one is gravitational constant. Gravitational constant is, we know our F equals to what? G m1 m2 over what? R square. So making G the Fourier formula, we have what? F R square over what? M square. So your G equals to what? You know first is what? MLT minus 2 times what? L square. Radius is in length over M square. Okay, so So we have let's come here. So we have what now? Our G now equals what? M minus 1, because M is M1 divided by, that's 1 minus 2, that's M minus 1, L 3 T minus 2. This is Gravitational constant. Okay, so now let's go to Planck constant. Planck constant is E equals to what? HF, while H equals to what? E over F. So E is in energy. Energy is mL square T minus 2 over, what's F? T minus 1. So equals to what? mL square T minus 2 minus 2 minus 1, that's minus 2 plus 1, that's minus 1. So this is the unit of Planck constant. Now let's go to the next one, which is Boltzman constant. Boltzman constant, I'll use B for it. Okay, B equals to, now let me just show you this. PV equals to KT. So this K is known as Boltzmann constant. Okay, so you can make K the subject of formula. K equals to PV over T. So PV is PV, if you know, and you know, remember that W equals to what? P, you can do it, but I don't want to P change in V. So PV can be equals to work done to, which is energy. You can do it out, we get the same thing, because okay, P equals to force over area times what? Volume. V is area times length. Area cancel area, so W equals to what? F times distance. So work done is same as work done, so you can just say is mL2 T minus 2 over temperature. Temperature is in theta. Okay, you have to note it. Temperature is in theta. Remember, we said the dimension of temperature is what? Theta. So in this sense, we can come and we can say that K is equals to mL2 T minus 2 theta minus 1. That's Planck constant. So we'll do others which are resistant. Okay, let me just, now PV potential difference equals to work done over charge. So work done is same thing as energy, which is what? mL2 T minus 2 over charge. Charge is, you know that charge is Q equals to what? IT. So IT. Okay, so equals to what? mL2 T minus 3 and I minus what? Minus 1. So I minus 1, that's potential difference. So that's potential difference. I do want to look for resistance. Resistance, remember, is what? Resistance is V equals to IR. So R equals to V over I. So all this one, mL2 t minus 3 I minus 1 over I. So we have m L2, okay, t minus 3 I minus 1 I minus 2. So now we go to capacitance. Um, capacitance, you know that Q equals to what? CV. Okay. C equals to Q over V. So if C equals to Q over V, that is C equals to what? I T over, I can't remember what voltage is. I think I should not have erased it. But I think it's M L, I think it's 2 T minus 3 I minus 2. If I can remember, if I don't remember, please correct it. So now be what? Capacitor will now be what? M minus 1 L minus 2 T 1 minus 3, that's T 4 I 2. So that's capacitance. Okay. So the last one is thermal conductivity that we'll do here. So you can do as many as possible. Thermal conductivity. So now this is where we are going to use both rate and gradient together. Remember I told you from the beginning that rate and gradient are very important. Rate is per unit time, while gradient is per unit length. So thermal conductivity says that rate of flow of energy, okay, rate of flow of energy, which is also Q over T. Q is quantity of heat. Rate of flow of heat equals to, is directly proportional to what? Is directly proportional to the area and then the temperature gradient. Rate of change of heat is proportional to what? Area and what? Temperature gradient. So we can say Q over T equals to K A T over what? Change in L. So this K